All right, today we are going on a journey deep, deep inside the atom, right to the very edge of reality to meet the fundamental particles that make up, well, pretty much everything you can see and touch. We are talking about quarks.
But let's kick things off with a real head-scratcher. What if I told you there's a building block you can never ever hold in your hand? A brick that can only exist as part of a wall, never by itself. That is the bizarre, absolutely fascinating world of quarks, and it's the central mystery we're going to unravel today.
So let's start with what we know. Everything around us, right? The stars, this planet, it's all made of atoms. That's our classic starting point for understanding matter, the stuff we learned in school.
And if we zoom in, way past those buzzing electrons, we hit this dense little core at the center, the nucleus. And that's packed with protons and their neutral buddies, the neutrons. For a good long while, we thought, okay, that's it. We found the bottom.
But science is never satisfied with the bottom. It's always asking, what's next? What's smaller? So, naturally, physicists started asking that exact question. Is a proton really the end of the line? Or is there something else hiding inside?
And that one question, well, it basically kicked open the door to a whole new chapter in physics. Because it turns out, protons and neutrons, they aren't fundamental at all. They're actually made of something even smaller.
So picture this. It's 1968, and scientists are basically firing high-energy electrons at protons like tiny little bullets. And what they saw was just incredible. The electrons weren't just bouncing off a smooth single object. No, they were ricocheting off these tiny, hard little points inside the proton. They had found something new, and they called them quarks.
Now here's where things get really, really weird. Quarks came with a property that just blew everyone's mind. See, up until then, every particle we'd ever found had an electric charge that was a nice whole number, like +1 or -1. Quarks, they completely shattered that rule. They have fractional charges.
And here's the beautiful recipe for a proton. We know a proton has a charge of +1, right? Well, that's because it's this little bundle of two up quarks, which each have a +2/3 charge, and one down quark with a -1/3 charge. You do the math, and bingo, it adds up to a perfect +1. It's such a strange but elegant solution.
But the story doesn't stop with just up and down. Oh no. It turns out there's a whole family of these particles, and they're organized in this very neat, very particular way.
So we've actually discovered 6 different types or flavors of quarks. They're grouped into 3 generations. The first generation, that's our familiar up and down quarks. Then you've got the second generation with the charm and strange quarks. And finally, the third generation has the top and bottom quarks. And as you go up through the generations, these particles get way, way heavier and a lot less stable.
And just to give you a sense of the scale here, check this out. The up quark, one of the building blocks of you and me, is incredibly light. The top quark, on the other hand, it's ridiculously massive for a fundamental particle. Its mass is about the same as an entire atom of gold. It's so heavy and unstable that it decays almost the very instant it's created.
As a quick little aside, ever wonder where that weird name quark came from? Well, the physicist Murray Gell-Mann, who helped dream them up, actually pulled it from this line in James Joyce's famously dense novel, Finnegan's Wake. He liked the sound of it, and that number 3 in the quote, well, it fit perfectly with how he thought quarks existed in nature.
So all of this brings us right back to that central puzzle. If these things are so fundamental, why can't we ever find one all by itself? This is the great mystery of confinement.
The official name for this is color confinement, and it's basically a fundamental rule of the universe. You will never, ever find a lone quark. They are permanently locked up inside bigger particles called hadrons, and protons and neutrons are just the most famous examples of these hadrons.
So what's keeping them prisoner? It's the strong nuclear force. And this force is unlike anything else we experience. Unlike gravity or magnetism, it actually gets stronger the farther apart you pull the quarks. It's like stretching some kind of cosmic rubber band. If you pull it too hard, all that energy you put into it just snaps and creates a brand new quark and anti-quark out of thin air. You don't get a free quark. You just end up with more particles.
Okay, so how do you even begin to explain a force that behaves like that? Physicists needed a new idea, and they came up with an absolutely brilliant one. A new kind of charge that governs this force.
They called this property color charge. Now, this is super important. This has absolutely nothing to do with the colors we see with our eyes. It's just a playful analogy for a type of charge that comes in 3 different varieties, which they decided to call red, green, and blue.
And this new charge comes with one simple, totally unbreakable rule. Only combinations that are color neutral or white are allowed to exist out in the wild. And you can do this in a couple of ways. You can take a quark of one color, let's say red, and pair it with an antiquark of the anti-red color. That makes a particle called a meson. Or you can grab 3 quarks, one of each color, one red, one green, and one blue. That combo makes a baryon, like our good friend the proton.
And this is why that color analogy is so perfect. You know how red, green, and blue light mix together to make pure white light? Well, in the subatomic world, a red, a green, and a blue color-charged quark combine to make a white, or color-neutral, particle that nature allows to exist. It's this beautiful rule that explains why they're always confined. Nature just forbids any lone color from getting out.
Okay, so we've got these weird, trapped particles with fractional charges and made-up color rules. Why should any of this matter to us, living our lives up here in the big world?
Well, here's the kicker. Despite all that complexity, the 6 flavors, and the 3 generations, all the stable matter in the entire cosmos is built from a shockingly simple recipe. Just 2 kinds of quarks, the up and the down, plus the electron. That's it. That's the whole ingredient list for everything you've ever seen. But I've saved probably the most mind-bending fact for last. Let's talk about the mass of a proton. You'd think, logically, you just add up the masses of the 3 quarks inside, right? Nope. Not even close. The actual mass of those 2 up quarks and 1 down quark, it only accounts for about 1% of the proton's total mass.
So where's the other 99%? It's energy. It's the insane amount of energy from the quarks rattling around inside and the binding energy of the strong force holding it all together. Pure energy, creating mass, just like Einstein's E equals mc squared said it would. It means that most of what you think of as you isn't actually stuff. It's the energy that's holding the stuff together.
And that leaves us with one last really deep question to think about. If the solid, tangible mass of our world is almost entirely just the energy of these invisible fields binding together nearly massless particles, what does that say about reality? What is matter, really?